Welcome to Chapter 14 about acids and bases. We want to start by just defining what acids and bases are. So the original definition for acids and bases historically came from Arrhenius, same Arrhenius of the Arrhenius equation for activation energy. And so Arrhenius's idea was defining acids and bases based off what they do when they're in water. And we actually have an updated definition that acids, when they go into water, they lead to the production of H3O plus ions. So say you have your water and you dissolve some HCl, hydrogen chloride, into there. That hydrogen chloride would react with the water to make this H3O plus. And you can see what's left over is the Cl minus. Traditionally, acids were thought of, Arrhenius thought acids were H+, and you may have already previously learned that acids lead to the creation of H+ in water, H+ aqueous. The thing is, H+ aqueous doesn't exist. If you have H+, that's just a proton floating around in water. We know that that's not actually accurate. What happens is, if that were to exist, it would immediately react with a water, latch onto the water, and create this H3O+, which is called hydronium. Hydro is like water, and nium actually is a reference to cations. So it's the cation form of water. It has an extra H+. So acids, hydronium, H3O+ is our ion that we want to be thinking about and associating with acids, whereas bases lead to the production of hydroxides, OH-. Traditionally, a lot of times when we think about bases, it's just like metal hydroxides, like sodium hydroxide. When it dissolves into water, because it's ionic, it separates out into those ions. So the sodium cation and hydroxide, you have increased the concentration of hydroxide, making this thing a base. So it is worthwhile to talk a little bit about some of the language surrounding this. Acid and base is the description of a compound. So nitric acid is an acid. Sodium hydroxide is a base. And so that is our description of when we say acid base, that would be, a property of a compound we have to be talking about. If we start to talk about mixtures, for example, nitric acid dissolved into water, we could call that mixture, that solution, acidic. So that would be an acidic solution. If you dissolve sodium hydroxide into water, that would make a basic solution. So you don't make a base when you dissolve sodium hydroxide into water, you make a basic solution. The sodium hydroxide is a base. Acidity or basicity is the name of that property. You will also see the word alkaline. It's kind of an old-timey word for basic that's still very commonly used. For example, alkaline batteries. We just don't really use it that much in the context of the chemistry lab, but alkaline or alkali, you'll see pop up a lot of places as a reference to basic things. So we want to discuss a little more this idea of what acids and bases are doing in water. So when we talk about acids in water, that they create this hydronium, well, how that happens is that an H atom leaves from the acid molecule and goes on to the water molecule. And so we can actually trace what happens in a sort of a mechanism of occurrence at the molecular level by kind of following where the electrons are. So those arrows that are shown here are the flow of electrons. So this lone pair on the oxygen atom is basically reacting. Those two electrons that were the lone pair on the oxygen atom have now become the bond between the O atom and the H atom. All those two electrons are donating in, whereas the two electrons that started in the bond on the hydrogen and the chlorine are now entirely the lone pair on that chloride anion. And so we can see it's this movement of H's. So one of the things that comes from this is when we're looking at formulas of chemical formulas, we can see in HCl, the H is first because the H is what makes it an acid. Acids inherently have these hydrogen atoms in the front, and that is what makes it an H. So when we write the formulas, we see the H in the front of the formula. There are, of course, complications with the formulas of acids. One of them is the organic acids. So organic, if we remember, means based around carbon. So acetic acid, CH3COOH. This is a condensed formula. You can see there's all the atoms are arranged to show the structure of the molecule, and the COOH actually corresponds to this part of the molecule right here. You'll note it's usually actually on the back of the molecule instead of the H being in the front. The H is at the end. That H right here, this small white sphere hanging off the edge, that is actually the acidic hydrogen. When it reacts with water, that is the one it loses. You will note that's where the hole is in the structure over here, and then there is nothing on this part of the molecule in the actual structure there. So COOH is an acid, and those hydrogens, that hydrogen at the back is the acidic hydrogen. These hydrogens here on the CH3, those are not actually acidic. Those aren't going to get lost or react as an acid. So bases produce hydroxide in water. That can happen via reaction, just like we see the creation of hydroniums. A common example would be molecules that contain nitrogen atoms that have a lone pair. So the canonical case is ammonia, NH3. It reacts with water to make ammonium and hydroxide. And so the ammonia, we can see if we look at the fluid structure, has this lone pair. And again, we can see that lone pair becomes the bond with a hydrogen atom. In this case, that hydrogen atom came from water, and the electrons that were forming the bond to the hydrogen now are a lone pair on the hydroxide. So this is a general pattern that is true for nitrogen atoms that have lone pairs. They can behave as bases in their molecule. And so that's a common characteristic or common feature that we see in those molecules. You will also note that the hydrogen atoms in ammonia were written at the end of the molecule. They're written at the back here to indicate that those are not acidic, right? This is not an acid. This is in fact a base. So we can put this together into kind of these ideas of moving hydrogens into a different, updated definition of acids and bases called Brønsted-Lowry. And the Brønsted-Lowry definition is not just based around what something does in water, but instead classifying individual reactions. So in a given reaction, an acid-base reaction, there'll be the transfer of an H plus from one molecule to another. So H plus is just a proton because that's just a hydrogen nucleus without its one electron. So it's just an H plus, that'd be a proton. And so in each reaction, you'll have one acid and one base on the reactant side, and they will donate an H plus to the other. So you can see we have the HCl that starts here as my acid. I can see the Cl is left over on the product side, but it has lost the H, and the charge also decreases by +1 because it's really losing an H plus. Conversely, the water, which is the base in this reaction, has gained an H, right? It's now H3, and it's plus. The charge increases by +1. And so when we're dealing with Brønsted-Lowry acid-base reactions now, we're talking overall about the two molecules that are participating in this reaction. We can see this is still a same description kind of as Arrhenius. It's just now you're recognizing the fact that the water is participating in the chemistry. The water as a base is receiving the H plus from the acid HCl. So there are always going to be two reactants. One will be an acid and one will be a base. Those are always reactant designations. And overall, we've now removed this. This is an inherent property of a molecule, right? We said before that, say, HCl is an acid. With the Brønsted-Lowry definition, in this reaction, HCl is the acid. So this is a type of reactivity. They're not inherent properties of molecules. A lot of molecules can behave as both an acid and a base, depending on the context. It's just this type of reactivity, a classification of a common type of reaction, a common change that we see among atoms. All right, let's get some practice analyzing some reactions. I got 3 reactions here, and I would like us to identify the Brønsted acid and base in each of those 3 reactions.
All right, so we've got some chemical reactions, and we want to know the acid and base. So when we're looking for acid and base, we want to be focusing in on the reactant. So I have HCl plus OH minus, that's becoming Cl minus and H2O. And so Brunstad just tells us it's the type of acid that we're looking at, this H plus. So what we really want to look at is basically the parts of the reactants that aren't hydrogen and see what the corresponding product is. So I have HCl, so I can see there's a chlorine in that molecule. And so I'm looking for the chlorine on the product side, so right here. So I can see that basically what this means is that the corresponding product is right here, the Cl minus. And we can see that what happened is it lost H. And we can see that the O in the OH corresponds to the water right here where it gained H. And so not just H specifically, but we can see that it went from being neutral to negative. And so that means it also lost a positive charge. OH minus went to positive, so it gained a positive charge. And so that means that the HCl, because it lost the H, is going to be the acid. And the OH minus, because it gained, is going to be the base. So we're looking for how did that H plus transfer? So then if we look, I got HSO3 minus plus F minus becomes SO3 2 minus plus HF. And again, we're looking for the non-hydrogen atoms and how they change. And one of the things we can even key in on is on this F, the F minus becomes the HF. One of the things you'll notice that F minus as a reactant contains no hydrogen atoms. That means it is literally impossible for this thing to be a base, an acid, because it can't donate an H, right? It can't lose the hydrogen, it can't donate it. So that means F minus has to be the base, which is consistent with the fact that the fluorine on the product side has an extra H on it, right? It gained an H plus. And we can see that this, which basically by process elimination, if this is the base in the reactant, this has to be the acid in the reactant. And we can see that it has in fact lost an H plus. It's donated the H plus over to the F minus. C5H5N plus H2. We can see the C5H5N looks a little, it's kind of there are hydrogens in there, but we can see that it gains a hydrogen over here. It gains that H plus. And so you'll note this is really written kind of awkwardly where the H is not paired in, it's written on the end. And the purpose of that is to show that this nitrogen atom is functioning as a base. It's one of those cases that's a nitrogen atom with a lone pair in that molecule. And it picks up an H and it attaches on to the nitrogen, and that's why this product is written in this way. So when we see N atoms like that, especially that are written by themselves, especially when there's no O in the molecule, that's likely a base. And this H2 is the acid, which we can see is consistent. H2O is the acid. It's consistent with the fact that the O has one fewer hydrogen on the product side. So we can look at reactants, figure out what is my acid and what is the base, or is it going to have one of each? And there's going to be that transfer of hydrogens.
One important thing about Brunstad-Lowry descriptions is that a molecule can behave as either an acid or a base depending on the context. In Arrhenius definitions, you're linked to water, just what does it do to water? It's a binary, it's either an acid or a base. But here we can see something like HCO3 minus, so bicarbonate. And so bicarbonate has a hydrogen in the front, like we associate with acids, but it also is an anion, which is a characteristic common among bases. And so we could react, say, HCO3 as a base here, where it reacts with HCl. It takes on a hydrogen, becomes the H2. It could also function as an acid, where it donates away a hydrogen and becomes CO3 2 minus. So it's donating that away. So you may have noticed in the lab, if you ever look in, say, the fume hoods, or really any lab, not just here at Lee College, there is usually sodium bicarbonate, a large jug of sodium bicarbonate. And that's actually why we use it for spills, because it is amphoteric. It can neutralize either dangerous acids or dangerous bases. And it can react and neutralize those compounds to become something more benign, right? You can deal with potent acids, large spills of acid, large spills of bases. You can react with them, neutralize them, and create something that's far less dangerous, far less reactive. And so that's why we use sodium bicarbonate, because it has both those. Instead of having to have, say, an acid to react with bases and a base to react with acids, we just need one thing. Sodium bicarbonate can pull double duty. Okay, welcome to chapter 14, getting started here. Looking for questions on participation 10-7. It's going to be due on Tuesday. On Wednesday, we'll have the midweek 7 homework due Wednesday about the set of videos. On Wednesday, we'll do determining KC lab. It's about chemical equilibrium. So if you're not liking chapter 14 so far, we're going to do chapter 13 stuff. We will also, before that, meet and do the chapter 13 participation follow-up. So it's going to look and feel just like the chapter 10 participation follow-up, just be about chapter 13 material. If you have any questions about anything, don't hesitate to reach out. Otherwise, welcome to chapter 14. Hope you enjoy it. See you in the next video.